Objective: learn the basics of spectroscopy with Fourier transformed infrared, their characteristics and the factors involved therein. Identify the main functional groups through different interpretation of FTIR spectrum.
Introduction. The spectroscopy is a very useful technique to determine molecular structures. IR radiation does not have enough energy to induce electronic transitions, as seen with UV. Absorption of IR is restricted to compounds with small energy difference in the possible vibrational and rotational states. For a molecule to absorb IR, the vibration or rotations within a molecule must cause a net change in the dipole moment of the molecule. The alternating electrical field of the radiation interacts with fluctuations in the dipole moment of the molecule. If the frequency of the radiation matches the vibrational frequency of the molecule, then radiation will be absorbed, causing a change in the amplitude of molecular vibration. This frequency depends on the atoms that conform the bond and their electronegativity. This allows use to measure the absorbance grade in different light frequencies and so determine the active groups of used molecule. The term infrared covers the range of the electromagnetic spectrum between 0.78 and 1000 mm. It is useful to divide the infrared region into three sections: near, mid, and far infrared. So, to understand the infrared spectroscopy, we need to define three concepts: transmittance, absorbance, and the law. If we define transmittance like the percent of original light intensity that was transmitted, we obtain the next equation. So, now we can define the absorbance like the less logarithm of transmittance. But the absorbance can be affected by some natural effects. A. Scattering laws in the solution. B. Reflection laws in the interface. C. Reflection laws by the big molecules. And D. Absorption by the container walls. So, we need to define an equation to describe it, an equation that considers the losses mentioned. This equation is called Beer law. Consider a simple container that has an area S with a large B and substance with concentration C, with a great absorption alpha. So, we can define use model consider that the photons are absorbed instantly. If we consider an area differential ds in which a photon was absorbed, if we divide this differential area between the total area S, we obtain the probability of photon capture. In other side, we can observe that if we consider a differential of intensity, differential of E sub x, like the photons captured probability, we can define the less differential of intensity between the total intensity, like the observed fraction of photons. Now, we can equate these two equations as follows. But we know that the area differential is proportional to the number of photons absorbed. So, we replace this in the equation. The finite leaves of the equation and integrating, we obtain transforming in the base 10 logarithm, replacing the number of particles between the volume by the concentration C, and regroup all the constants in one, we obtain the Beer equation that defines the absorbance in function of the concentration, the molar absorption and the large of the cell, B, or in function of the intensities of the rays that enter in the sample and get out.
Calibration. A sample of polystyrene was used to determine the good operation of the spectrometer. This sample includes a graphic with its corresponding spectrograph and IR. The comparison between this graphic and the graphics obtained by the real spectrograph made in IR spectrometer provides a good comparison of the spectrometer sensibility. Some equipment need that the range of observation be established, so we left that the laser light be measured with sample and establish this point like the 100% of absorbance. Next we close to tally the objective and establish this measure like the 0% of absorbance. Experimental part. Materials: Agatha mortars, IRTF spectroscopy, cell of sodium chloride, industrial grade acetone, Pasteur pipettes or capillary tubes, reactives: potassium bromide, sodium acetate, benzoic acid, ethanol, aniline.
Potassium bromide pellets are easy to make if a few simple rules are followed. First, heat the envelopes and the body of the die set before you make your pellet. This makes them as dry as possible. Second, use dry potassium bromide powder. Third, make sure that the envelopes, the die set, and the powder are of the same temperature. Hot powder and cold envelopes will produce a cloudy wet pellet. Using too much potassium bromide powder is one of the most common mistakes. Use as little potassium bromide powder as possible. Usually, use barely enough to coat the envelopes of the die set so that the face of the envelopes is completely and evenly covered with a very thin coat of powder. To compress an excessive amount of powder requires considerably more force on the press than is required if the proper amount of powder is used, and if inordinate force is not applied to the excessive powder chairs, the pellet will either wedge or contain white spots. Laboratory press are used for a variety of tasks, but the bulk of the application involves pressing simple pellets from a matrix of potassium bromide and organic samples for infrared spectroscopy.
Manufacture the pellet.
The method is to grind a quality of the sample with a special purified salt. In this case, we use potassium bromide finally. This sample is mixed with potassium bromide in Agatha mortar, proportion 1:10. We use an Agatha mortar and not porcelain because of the ability to control the grind and also to virtually eliminate contamination from the mortar and pestle set itself. This is probably the most ancient device one is likely to find in a modern scientific laboratory, and with this we look for a homogeneous blend between the sample and potassium bromide.
For the practice we use an hydraulic press. This is a machine in which a large force is exerted on the larger of two pistons in a pair of hydraulically coupled cylinders by means of a relatively small force applied to the smaller piston. That produces a force about 15 tons UDE to make high quality 13 mm pellet used for infrared solid sampling. How it works the hydraulic press? The pressure throughout a closed system is constant. One part of the system is a piston acting as a pump. with a modest mechanical force acting on a small cross-sectional area. The other part is a piston with a larger area, which generates a correspondingly large mechanical force.
After getting the pellet with the press, this introduces it into a spectrometer, and we verify that the light beam passes through the pellet and closes the spectrometer. Then the software analyzes the sample and returns a graphic with different spots representing compounds found in our sample. Given our sample in the spectrometer, we start the software, beginning optical instrument, factory second, main FTOS system, view 1.0. Press the collect button, and from there choose the option transmittance spectrum. The interpretation of this spot is excused in the IR date bus of several compounds. Below are the images that were obtained in the spectrum. Here we see a graphic of probable sample. In this part we can find a spot that belongs to an alcohol group. Also, we can find in this site the fingerprint that is common for each compound. Here we found the spot of carbon dioxide that always is present because that is in the air.